Reciprocating pump is used for comparatively lower flow rate and higher pressure rise as compared to centrifugal pump. And so I have selected today the topic of discussion is working principle of reciprocating pump. In this video, we'll see about the construction and operational philosophy. In addition to this, we will also see the effect of acceleration head of the fluid and pipe friction losses head on the PV diagram. And we'll also see how PV diagram is simplified based on certain assumptions. So let's start the discussion of working principle of reciprocating pump. This is construction of reciprocating pump. So this is a crank shaft which as shown is rotating in anti-clockwise direction. It has inner dead center IDC and outer dead center ODC, and radius is R. Connecting rod is connected to the piston, and this is a cylinder, and this is piston arrangement. It is shown as a single acting pump, so it has one suction valve which is connected to the cylinder, and another is a discharge valve which is also connected on discharge side. The suction pressure is measured this location and discharge pressure is measured at this location. So we'll see we have also considered some pipe losses and acceleration head losses at the suction as well as discharge side. So recip pump works on the principle of compression process just like just like recip compressor, but the fluid is incompressible, so pressure rise occurs without any actual fluid compressions. So compression process is accomplished by the piston and cylinder arrangement as shown in the figure. Piston is connected to crankshaft through the connecting rod. Rotary motion of crankshaft is transmitted to linear motion of piston. In one revolution of crankshaft, piston will move twice in the cylinder. So a stroke length, as I said, is a distance between IDC and ODC. So stroke length will be certainly the twice the crankshaft radius, and cylinder is equipped with suction and discharge valves, and these valves are really check valves or non-return valves and works on the principle of differential pressure between the cylinder and piping. So suction valves opens when the cylinder pressure is lesser than the inlet pressure and closes when it is equal to or more than inlet pressure. Similarly, discharge valve opens when the cylinder pressure is more than outlet pressure and closes when it is either equal to or less than outlet pressure. So in this way, fluid is taken inside the cylinder, pressure rise occurs, and then discharge to the discharge pipe. So let's see some derivation about acceleration head and friction losses head. So how it has been derived. So let's assume crank shaft radius is on R. A stroke length is a L, which is 2R in meter. Radius is also in meter. And an angular speed is of the crank shaft is omega radian per second. So in time t from IDC, it starts for time t, let's say t, then angular displacement will be omega t radian, so which is equal to theta. So you can replace theta is equal to omega t. So length of suction and discharge pipe is ls and ld in meter. Diameter of suction and discharge pipe are ds and dd in meter. Cross section area of cylinder, suction pipe and discharge pipe are respectively we have denoted as a, as and ad in meter square. Velocity of piston, velocity of fluid in the suction and discharge pipe are v, vs and vd in meter per second, and acceleration of the fluid in suction discharge pipe is as and ad meter per second square. So displacement x from the inner dead center IDC is written as x is equal to r minus r cos omega t, which is written as r minus r cos theta in meter. Velocity of piston v is equal to differentiation of x, which is coming as omega r sine omega t is equal to omega r sine theta meter per second. Velocity of fluid in suction pipe Vs is equal to A upon As into omega r sine omega t is equal to A upon As into omega r sine theta meter per second. Similarly, velocity of fluid in the discharge pipe Vd is equal to A upon Ad omega r sine omega t is equal to A upon Ad omega r sine theta meter per second. So acceleration of the fluid in the suction pipe is again differentiation of velocity of suction, which is coming as A upon As into omega square r cos omega t is equal to A upon As omega square r cos theta meter per second square. Similarly, acceleration of fluid in the discharge pipe Ed is equal to differentiation of velocity in discharge, which is coming as A upon Ad into omega square r cos omega t is equal to A upon Ad omega square r cos theta meter per second square. Now acceleration head is defined as mass into acceleration is a force divided by cross section area is pressure into divided by density is the head. So mass can be written as density into cross section area into length is a mass into acceleration head is this divided by cross section area into density. So density and cross section area is cancelled out. So acceleration head is equal to length into acceleration joule per kg. So acceleration head in suction pipe can be written length is ls. Acceleration is written as A upon As into omega square r cos omega t is equal to ls into A upon As into omega square r cos theta joule per kg. Acceleration head in discharge pipe will be Ld into A upon Ad into omega square r cos omega t is equal to Ld into A upon Ad into omega square r cos theta joule per kg. Note that acceleration head is a maximum at the starting point. So theta is a 0 is a maximum. 0 at the midpoint, theta 90 degree, and negative at the end point for suction pipe and discharge pipe. Now friction loss head or pipe friction loss head. So velocity of fluid in suction pipe, as you know, Vs is equal to A upon As omega r sine omega t is equal to A upon As omega r sine theta. Velocity of fluid in discharge pipe A upon Ad into omega r sine omega t is equal to A upon Ad omega r sine theta meter per second. So friction loss head in suction pipe is equal to F is the friction loss factor. So F into Ls upon ds into Vs square upon 2 joule per kg. So putting the value of Vs, this is a friction loss head. Similarly, for the friction loss head in discharge pipe, F into Ld upon dd, Vd is Vd square upon 2. So putting the value of Vd, this is the friction, sorry, this should be discharge pipe. So friction loss in discharge pipe, not the suction pipe, should be F into Ld upon dd into A upon Ad omega r sine theta complete square upon 2 joule per kg. So it is evident that the friction loss head is 0 at the starting point, maximum at the midpoint, and 0 again at the end point for suction and discharge pipe. So PV diagram, pressure volume diagram, x-axis is the volume, y-axis is the pressure. So PV diagram for suction and discharge pressure as indicated with the consideration of acceleration and friction pipe loss head. So this is stroke volume VL. So this is inlet pressure measured here and P2 is measured here. So these are P1 and P2 pressure, and P1 dash, this loss is considered as the pressure drop across the suction wall, And similarly, P2 and P2 dash is a pressure loss or pressure drop across discharge valve. So these are the losses, and this straight line is the suction acceleration head, and this is a discharge acceleration head, and this curve is pipe friction loss at suction, and this is a discharge pipe friction loss. So these are the PV diagram for consideration of acceleration head and friction loss head, along with the pressure drop of suction valves and discharge valves. Now, PV diagram without acceleration head. Acceleration head decreases the pressure at a starting point. You can see, you have seen this, and gains pressure at the end of the point for both suction and discharge. So work head point of view, this can be eliminated because it has no impact on the work head. So acceleration head is neglected or removed. However, acceleration head can cause cavitation in pump and should be taken care during the design of the pump. PV diagram without acceleration head but with the consideration of pipe friction losses head is shown again. So this is volume, this is pressure. So this is again P1 is a pressure, P1 dash is a pressure. So pressure drop across suction wall, similarly for discharge, and this is the pipe friction loss for suction. This is pipe friction loss for discharge. Now PV diagram with inlet and outlet pressure measurement closer to cylinder. Now you see, now measurement is closer to cylinder just before the valves. This is P1 and now this is P2. So if inlet and outlet pressures are measured or installed close to the cylinder, then the pressure takes care of maximum pipe friction losses, head, etc. That means moment you take this pressure, that means all the piping losses has been considered along with this pressure. And similarly for the discharge side, all the piping losses and required pressure is considered as a P2. So now P1, P2 is the measure closer to cylinder. So now we are left out is pressure is only pressure drop across suction valves and pressure drops across the discharge valves. With that measurement, so inlet and outlet pressure includes all the losses in suction and discharge pipe respectively. The only left out pressure left out are pressure drop are suction valves and discharge valves. So PV diagram is now simplified. So this is P1 measured at closer to cylinder. P2 is a pressure measured on closer to cylinder on discharge side. This is on suction side. And this drop is the pressure drop across suction wall, and this is pressure drop across the discharge valves. So this is the simplified PV diagram of reciprocating pump. Now double acting reciprocating pump. So double acting reciprocating handles the mass double of as compared to the single acting reciprocating pump. So it has two inlets valves and two discharge valves. So fluid comes in and goes to both the inlet and goes out on the both sides. So in one movement of this piston, fluid is coming this side, filled up, and then compresses. So it will pass to this discharge delivery valve. So in second return, this piston compresses this side of fluid and then presses create pressure and discharge on this delivery valve. So in double acting reciprocating pump, it handles the mass is double of single acting reciprocating pump. So now what is single acting cylinder and double acting cylinder? In one single acting cylinder, in one revolution of crankshaft, two stroke piston, and only one time fluid is taken inside the cylinder, pressurized and pushed out in discharge system. So you can see this is valves, one suction, one discharge. This is single acting. Similarly for double acting cylinder, it has two valves suction, two valve discharge. One revolution of crankshaft, twice the stroke of the piston, and fluid is taken inside the cylinder twice, pressurized and pushed out in discharge side. Then it is called the double acting cylinder. So in double acting cylinder, mass handle of the fluid is double of the single acting cylinder. So this is all about the working principle of reciprocating pump. So let's say about the main parts of the reciprocating pump. So crankshaft, connecting rod, piston, cylinder, suction, discharge valves. Crankshaft is driven by a driver like motor. This is a main component which transfers power from driver to piston. Connecting rod is plays the vital role which converts rotary motion of crankshaft into the linear motion of piston rod. Piston and cylinder. Cylinder is the main component where pressure rise takes place. Suction discharge was installed on the cylinders, and piston is responsible for pressure rise of the fluid in the cylinder. Suction and discharge valves. Suction valves are installed at the inlet of cylinder and discharge valves are installed on the discharge side of cylinder. Valves are spring-loaded check valves and operates on differential pressure across it. So when the cylinder pressure becomes lower than inlet pressure, suction valves opens up and closes when cylinder pressure becomes equal to or more than inlet pressure. Similarly, when the cylinder pressure becomes more than discharge pressure, discharge valve opens and closes when cylinder pressure becomes equal to or less than discharge pressure. So this is how suction and discharge valves operates. Now volumetric efficiency, you can see the PV diagram, simplified form of PV diagram. So volumetric efficiency defined as the ratio of inlet actual volumetric flow divided by stroke volume. So volumetric stroke or stroke volume is equal to actual inlet actual volumetric flow divided by volumetric efficiency. Hydraulic efficiency is defined as the ratio of hydraulic head and actual head. So hydraulic head is defined as the ratio of pressure rise, that is discharge pressure minus suction pressure, and the density of the fluid. So hydraulic head is equal to written as or expressed as discharge pressure minus suction pressure bracket close divided by density of the fluid is called hydraulic head. And stage power. The stage power has a relation with mass flow rate, hydraulic head, and hydraulic efficiency, and it can be expressed as stage power is equal to mass flow rate into hydraulic head divided by hydraulic efficiency into 1000, where stage power in kilowatt, mass flow rate in kg per second, hydraulic head is joule per kg, and hydraulic efficiency is constant. So thank you and hope you will enjoy this session and understood the working principles of reciprocating pump and main components used on how main component of the reciprocating pumps. So thank you and thank you for watching.